When you look at this photo, your brain immediately says, that's a cat. You don't think about colors, shapes, or pixels, you simply recognize it. But computers don't have intuition. They don't actually see the way we do. So what does an AI see? If we keep zooming into this image, eventually the cat disappears. The fur disappears, the eyes disappear. Everything turns into a giant grid made up of tiny squares called pixels. To us, they're invisible, but to a computer, they're everything. Each of those tiny pixels is just a collection of numbers. Now, here's something interesting. You might think every pixel stores a color, but it actually stores three separate values. One number tells the computer how much red there is, another tells it how much green, and another tells it how much blue. Every single color in every digital photo is created by combining these three channels together. So instead of seeing a picture of a cat, the AI receives three enormous matrices of numbers, one red, one green, and one blue. We now have a tiny 5 by 5 image. In reality, images are much larger, but keeping it small makes the math easier to see. Every square here is one pixel, and every pixel stores three numbers: red, green, and blue. A convolutional neural network doesn't process the whole image at once. Instead, it looks at a small region called a patch. Here, we're selecting just a 3 by 3 section from the image. Since every pixel contains red, green, and blue values, this small patch actually contains 27 numbers arranged as a 3 by 3 by 3 cube. On the left are the pixel values from that image patch. On the right is a convolution kernel. These aren't pixel values, they're learned weights. During training, the neural network automatically adjusts these numbers until each kernel becomes good at recognizing a particular visual pattern, such as an edge, a corner, or a texture. Now the actual convolution happens. Every pixel value is multiplied by the weight directly above it. First the 9 red values, then the 9 green values, and finally the 9 blue values. That's 27 multiplications in total. Once they're all multiplied, the results are added together to produce a single output number. In this example, those 27 multiplications and one final sum produce the value 235.8. This single number represents how strongly the image patch matches the pattern stored inside the kernel. A larger value means a stronger match. A smaller value means the pattern is less likely to be present. But we've only analyzed one tiny patch of the image. The network still needs to examine every other location. So next, this exact same kernel slides across the image, repeating the same calculation again and again, building up an entire feature map. A single filter can only detect one type of pattern, so CNNs learn many filters. Each creates its own feature map, giving us a richer representation of the image. One filter might detect edges, another might find curves, another might respond to textures, each highlighting a different visual pattern. One image goes in. 64 learned filters process it in parallel. The result is 64 feature maps, each highlighting a different visual pattern. This is where deep learning gets its name. Early layers detect simple patterns. Deeper layers combine those patterns into increasingly complex features, until the network can recognize an entire object. The final layer converts everything the network has learned into probabilities. Each value represents the model's confidence for a different class. Here, it's 99.7% confident this image is a cat. And that's how AI sees an image. If you enjoyed this deep dive, don't forget to like, subscribe, and I'll see you in the next one.